So welcome to this webinar on Exascale matrix factorization using machine learning on supercomputers to find new drugs. I've been told that I should remind you that there's a question box somewhere in the GoToWebinar control panel where you can type in your questions, and then John, the organizer, he will make sure that I see those questions and I will answer those after the webinar. So I'm Tom, I'm from the Exascience Life Lab at IMEC, and what we do is we help pharmaceutical companies with their high-performance data analytics problems. And a couple of years ago already, the pharmaceutical companies, they came to us and they showed us this slide, which shows the whole process of drug discovery and drug development, starting from identifying a protein target. So usually when they want to tackle a drug, they look for a protein in the body where they can influence. When they want to target the disease, they look for a protein target in your body which they can target with a drug where they can influence the disease. So the first thing they do is look for a protein target, and then they look for a molecule that binds to that protein such that in that way they can influence the disease. They optimize the molecule, they optimize the target, and then they do tests. First, they do tests in the lab, and they do tests with animals, and then do large-scale clinical trials on sick people and then on healthy people. And the problem they have is that this whole process is expensive. Not only is it expensive, like it takes 5 years for the whole cycle, and it costs like 1 billion euros or $1 billion to come to the final actual drug on the market. It's not only that expensive, it's even more expensive because a lot of the drugs fail. A lot of the drugs are, it turns out that when they do the tests on the large scale of people, the clinical trials, the drugs fail mostly because of lack of efficacy, meaning that the drug is not effective, meaning that it doesn't reach the right part in your body, that it gets diluted, or that it attaches to some other protein which they haven't foreseen. Or the other way is where it can fail is that it's toxic. There's some negative side effects that makes that they cannot use this drug. And it seems that the trend is towards this more and more of these drugs failing in the later stages, in the sense that they spend 1 billion euros on this drug, and then only one out of 10 drugs actually work in the end. So it's not 1 billion euros, it's 10 billion euros per drug. And this is really a problem. And they came to us and they say, we want more potential targets, more potential molecules that we can use. And we want to use machine learning to predict in the very early stages whether the drug will be effective, or the molecule will be effective, or that it will be toxic. And then we come to the area of compound activity prediction, which is actually just that. You have a big matrix, or a pharmaceutical company has a big matrix of all the compounds they tried already, and the targets that they tried is on the protein targets in your body in which they tried to get the chemical compound. You have this big matrix on the right-hand side with like millions of chemicals and thousands of protein targets, and the pharmaceutical companies have lots of data, but still the matrix is only 1% full. They only know for less than 1% even of the matrix whether that chemical compound binds to the protein targets. And even worse, it's most of the examples that they do know are negative examples, meaning that they know that the chemical compound does not bind to the protein target. And they're looking for positive examples where the protein does bind, or where the chemical does bind. So what they want to do is they want to use machine learning to fill the whole matrix to make predictions for unknown combinations of chemical compounds and protein targets. And this is very similar to what Netflix and Amazon wants to do, except they don't want to make predictions on compounds and on protein activity, but they want to make predictions on whether a certain user would like a certain movie, in the Netflix case, or in the Amazon case, what kind of recommendations that they can make for when somebody has made a purchase at Amazon, what other things they can recommend. So a lot of these algorithms that we will see, or the main algorithm that we will see, is actually coming from the Netflix area. So they came to us and they say, can we do a project together to try to use machine learning to do compound activity prediction? So we set up a European funded project, or we prepared a European funded project, which became the ExCAPE project, which ran for 3 years. It finished last year. And there we brought together the people from the pharmaceutical industry working on the data preparation and the benchmarking. So in the project itself, there was AstraZeneca from Sweden and Janssen from Belgium as the 2 pharmaceutical companies working on the data itself. And then we had deep learning and matrix factorization experts, so people working on the machine learning from the UK, from Finland, and from Austria. And IMEC, together with Intel and IT4I, the Czech National Supercomputing Center, were in there to work on the high performance aspects, to make sure that the predictions were possible to make in a reasonable amount of time. Because this was really one of the problems why they couldn't tackle this compound activity prediction on their own. There was simply too much data, and building those models to make compound activity prediction on a regular system was not possible. They really saw that they would need high performance computing for this. There was already previous work on compound activity prediction, but previously they were never able to tackle the matrix, the matrix, the known matrix, the known activity matrix completely as a whole. They were only working in the past on single targets. So what they wanted to do, they were looking at one target, and they were looking at compounds for which they had known data, and then based on similarity with other compounds, they were trying to make predictions for the other compounds. Right? They were looking at compound similarity to make predictions on a single target. What the ExCAPE project wanted to bring, one of the major things was multi-target chemogenomics, where you build one single model for the whole matrix. And the other thing which the project really improved on chemogenomics was on using not only the activity values, but also using compounds features. Looking at the shape, the 3D shape and the 2D shape, or even at images of the compounds, using that to enhance, to make the model better and to make better predictions. So, and as you already saw on one of the previous slides, one of the algorithms that we used was deep learning, but the other one, I guess everybody knows deep learning, but the other one, which is a lot less known, that one is called matrix factorization. So most of this talk will be about how to optimize matrix factorization specifically or not so specifically to do compound activity prediction. And this is actually one of the winners of the Netflix prize. Netflix, they do every once in a while, they set out a competition where the goal is to find the best algorithm to do user movie rating prediction. And this was one of the winners in the late 2000s. And the matrix factorization starts from a given R matrix. It's called R in this case because it's representing movie ratings. And what you do is to build a model for these movie ratings to make predictions for unknown ratings, is to decompose this matrix R into 2 matrices U. U is the user matrix, it represents the users, and V is the movie ratings representing the movies. And you can make, let's say you make these 2 U and V matrices. If you want to make a prediction, you take a single column of U is representing a user, and a single row of V is representing a movie, and you make an inner product of a given user with a given movie to make a prediction. right? So there are as many columns in U as there are users, and there are as many rows in V as there are movies. And the second dimension of U and V is K, which is a relatively small number. So there are, K is like order of 64, 100 maybe. So that makes it tractable to actually store these U and V matrices in memory. You can never store the complete products. If you would multiply for the problems that we were looking at, if you would multiply U with V and try to store that, this would never fit in your memory, in your computer. It would take like hundreds and hundreds of gigabytes of memory, right? So it's important that the second this K is a quite small number. So this algorithm that we use to construct this UMV, to construct this factorization, is called BPMF. It's quite simple. You can write it down in 25 lines of Julia code. We translated this code into C++ using the Eigen Matrix library. It's still only 35 lines. That's good. It also predicts quite well. It uses a Bayesian method, and the main thing you should remember from that is that, at least in this context, this means that you not only get one prediction, you get a whole distribution of predictions, which gives you a confidence interval, right? You can see if the predictions it's giving are far apart, that means that your model is not very confident on those predictions. On the other hand, if the predictions are close together, that means that those predictions are quite accurate. The bad thing about this BPMF algorithm is that it's very slow. We did some estimates, and the Julia prototype would need to run 15 days on the industrial data that we had. So we really needed a much faster version of this BPMF algorithm. So we, the HPC experts in the XGAPE consortium and the XGAPE project, we sat together and we did many optimizations to this code. We did algorithmic optimizations, we did data locality improvements. We made a multi-core version using OpenMP and TBB, taking into account load balancing and data locality optimizations again. And then we also did the multi-node implementation using MPI and using GASPI with asynchronous communication. I'll explain a bit, very little bit about the multi-core implementation, but I'll go into a lot more detail into the multi-node implementation and what is GASPI. And then I'll explain how the POP CoE helped us into assessing the performance bottlenecks and then helping to optimizing those performance bottlenecks. So let's go first into, well, this slide, it shows basically everything you need to know about the BPMF algorithm in terms of what you need to know to do load balancing, to do communication. So what it shows is that, first of all, in terms of parallelism, you can update, so it's an iterative algorithm, meaning you update users, and then you update movies, and then you update users, and then you update movies. So you iteratively update U and V. And the thing is, you can do all of the users in parallel. So there are no dependencies in between. For one iteration, one update, there are no dependencies between the users, but the users depend on the movies. So you need to update all users, and you can do that in parallel, and then you need a kind of a hard barrier, and then you can update all movies. And this slide shows like the dependencies to updating this one movie, which is highlighted in purple. So what do you need for those to update this one movie? Is you need all the ratings for that movie, which are highlighted in blue, and then you need in light blue, and then you need all the users that have rated this movie, which are the vertical column vectors in the U matrix highlighted in dark blue. So this already shows two things. One is it shows load balancing. If one movie is very, very popular, that means that movie is going to need a lot more data accesses because you need a lot more accesses to you, and you also need a lot more computations. So the popular movies, if you have a large distribution between popular and not so popular movies, you need to make sure that you do your load balancing correctly, because the popular movies will take a lot longer than the not popular movies, right? And this is a known problem in graph. There are lots of graphs which have this property, and it's called the power law graph, that you will have a very few nodes in your graph with a lot of edges, and a lot of nodes in your graph with very few edges. So, and the other thing which this already shows is that it's communication. Since you can do all users in parallel, you can distribute these users across your different cores or your different nodes of your system. But as soon as you do that, you will cut across one of those lines that are shown, one of those dependency lines. And if you cut the line, that means you will induce communication, right? If you cut one line, that means that for the update this movie, you'll need to transfer those users that have rated this movie from one node to another node, unless those users and those movies are, of course, located on the same node. As I said, we did an implementation using GASPI. I don't think many people, maybe in this community, many people know, but still everybody or most people I know, to do node-to-node communication, most people in HPC use MPI. And we've also done an MPI implementation of BPMF, and I will talk about that one a bit later. But first, let me introduce GASPI. So have a look at the picture on the right-hand side. And basically what GASPI does, it's a kind of PGAS API. It's a PGAS implementation in the sense that it's partitioned. So you have memory segments, so-called GASPI segments, which is allocated memory allocated memory on different nodes of your system. And the GASPI API allows you to asynchronously transfer data from one segment on one node to another segment on the other node. This is nothing spectacular, right? That's what you do with MPI. You transfer data from one node to the other node. The good thing about GASPI is that it's not only lightweight, it's very lightweight, so you really have very limited overhead from GASPI. That's one good thing. But the most important thing is it's asynchronous. So you do a GASPI write, and you give it a local pointer and a remote pointer in a way of speaking, and a size, and it will transfer the data from your node, the local pointer, to the remote address on the remote node. And it does this completely in the background. You do the request to the library, and you immediately get the return from the library. And then if this function with this request is successful, that means that the request will be handled somewhere in the future by the GASPI API, right? And you can do many requests, and all of these requests will be handled very efficiently by the networking hardware. And in the meantime, you can continue with your computation. So this is very good way to overlap communication and computation. It's a very good way to keep all of the components in your supercomputer busy all the time. And then later on, when you finished when you finished a whole bunch of communication requests, what you do is you do a GASPI notify for example, to the same node, to the same remote node, and you guaranteed the remote system can wait for notification, or can check whether a notification has arrived. That's the blue line on the right-hand side. And it's guaranteed that the notification will arrive after all of the writes have arrived, right? So you know that the data has arrived when the notification has arrived. And this allows very easily to, allows for a style of programming which kind of forces you to do communication as early as possible and to do as much work as possible while the communication is happening in the background. It's multi-threaded, it's thread-safe, the GASPI library, and it's interoperable with MPI, meaning that it will allow you to do, if you have an MPI application, you can take parts of that MPI application, which are the bottleneck, and transfer those parts of the application to use GASPI, and you get a very good speed up. If you do it right, you'll get a good speed up. The GPI2 is an implementation, and it's available open source, so you can try it. You'll need InfiniBand, but it's also supported on quite a number of the supercomputers in Europe. For example, in many of the sites in the UK or in Germany or in France, you will have this GPI2 implementation installed. So as I said, so this is about GASPI. As I said, how do we do parallelization? You do parallelization by across several nodes by splitting. In this case, it shows splitting the users across multiple nodes, and then each of the nodes is responsible for computing parts of the U matrix. And you can also split the V matrix. And this is very straightforward to do with GASPI because it's very lightweight. You will have a lot of messages because the U matrix, you'll have one message for one vector or one user which you compute, and then you need to send the updates of this U matrix to all the sites which require this. So you'll have a lot of small messages, but doing it this way allows you to make to send your data as early as possible. As soon as you update the user, compute a new user, you can send it to the nodes that require this update. And that allows you to have the communication already done as early as possible while you're still updating new users, right? While with MPI, we also, as I said, we also did an MPI implementation, and we had, well, at that time, I was having a lot of problems with MPI. I guess many people will there might be people that do not agree with me, but I find MPI very difficult to use. It's a very thick standard, hundreds of pages, and I wasn't really familiar with all the new features of MPI at that time. I studied different ones. I studied asynchronous communication using iSend and iReceive. I did an implementation of MPI put using MPI windows. I did a simple broadcast implementation, of course, a simple implementation of the BPMF with MPI using only MPI broadcast, and of course that doesn't scale. So but this is one of the downsides of MPI, that there are many different possibilities, and I wasn't sure which one wasn't the best one for this case. The other things which were challenges using MPI was that it's at that time had a high overhead when you wanted to use MPI from multiple threads, and also high overheads in general. It takes a lot of CPU cycles to send a single byte of data, right? So that said, what we found out was the best way of working with asynchronous communication in MPI was to use a buffered iSend iReceive. So we would never send single users or single movies to the nodes that would need those user or movies. We would always buffer those into multiple movies at a time for a certain destination. And then once the buffer was full, we would send it using MPI iSend, and we would receive it using MPI iSend iReceive. And this was the implementation that worked the best. So let's have a look at some of the results. So what this slide shows is so this is a public data set, relatively small in that sense, 20 million ratings for 130,000 movies and 130,000 users, more or less. On the x-axis, you have the core count and the node count. It's a strong scaling experiment. And then on the y-axis, you have performance. And ideally, you should get the orange line, which is 100% parallel efficiency. Every doubling of the number of nodes gives you doubling of the performance. But this is a very difficult problem to scale, since every time you double the number of nodes, you split your computation in half and you almost double your communication costs. But still, the GASPI implementation performed quite well, so that's the brown curve, while for the MPI implementation, that's the MPI ICEND, the green curve, that was tailing off quite rapidly. And we looked at this, and one of the main reasons was that it's, well, there were two reasons, as I already said. You spend a lot more time in cycles to send a single MPI message. You spend a lot more CPU cycles in MPI, in the library. And the next thing is that apparently MPI is a lot less capable overlapping communication and computation. If you look at the right-hand side first of this graph, for 128 nodes, so the maximum, you see a large orange part. And this is the time for that simulation or that experiment where we spent time where both the CPU as well as the networking hardware is busy, where both the CPU is doing the compute and the networking hardware is doing the communication. So the orange part is effective time where you're able to overlap communication and computation. While on the right-hand side, you see a lot larger gray part, which is telling you that most of the time you spent is actually only doing communication. And the blue part and the orange part, where you do also computation, is a lot smaller. So that's why the GASPI implementation in this case is a lot better. So if you have questions about this, feel free to type them into the question box, and I'm happy to answer them later at the end of the presentation. So how did the POP CoE help us? So I tried to put in order the HPC expertise in the XGROOST consortium. And I would say, like, going from least experienced with HPC, the pharma partners, and then the machine learning partners, and then the HPC partners, for example, IMEC and IT4I, we were inside the XGROOST consortium, we were the most experienced with HPC. But I would say the POP CoE, that there you have a lot of partners in there which have even more experience in the very technical details of some of the libraries or some of the tools. They have good recommendations on how to use and what features to use from MPI for OpenMP. So we learned a lot from the POP CoE. We learned how certain tools that we haven't had an experience with, like we had used X-ray and Paraver. We learned how to use OpenMP tasks, and they told us how to do MPI asynchronous collectives, or actually they did this for us. So what they did was, first they helped us with an audit of the BPMF code. They used X-ray and Paraver to quantify the load imbalance. So if you look at the curve on the right-hand side in the top, you see a lot of lines. Blue lines means computation, and the dark blue lines, and you see there's one very long dark blue bar. I guess this is Star Wars or something, or some other movie, Titanic, for example. So that one is actually, it's dominating the execution time, or dominating the computation time. All of the other threads are waiting for this one thread to finish its update to this one very popular movie. And the solution for this problem was to introduce another level of parallelization, to break down this one popular movie or these popular movies into smaller chunks, and to have another level of parallelization when you have a certain threshold. Let's say if you're for one movie, there's more than n number of ratings, and then you need to determine the best value of the rate of this value n. And then you break, if this movie has more than n ratings, you break it up into smaller tasks. And we use POP CoE helped us optimize this code, and they used OpenMP task for this. And then after all these optimizations by us and by the POP CoE, it turned out that the collectives, so we have a lot of point-to-point communications in BPMF, and those are the most important communication types. But you also have some collectives, broadcast, gather, scatter operations. And after all the optimizations on the point-to-point, the collectives were the bottleneck. So they also helped us by introducing asynchronous MPI collectives, and they also gave us a speed up in the BPMF codes. So these are so the POP CoE, we had one audit report, and then we had two proof of concepts. In two proof of concept implementation, both of them we integrated in the code itself. So that's really nice. So let's come to the conclusions of this optimizations of BPMF. So as I said, the single node Chule implementation, we estimated it would take like 15 days to run. With single node C++ with TBB or OpenMP implementation, with GASPI for multi-node, this whole runtime would go down from 15 days to 5 minutes, which allowed us to do a lot more experiments, iterations, large-scale experiments, or include the features that we wanted, like compound shape information or compound features. And as I said before, load balancing is important, and communication hiding or asynchronous communication hiding. Asynchronous communication is important. If you're interested in the code, it's available open source. It's on GitHub. There are instructions. There's a tutorial. It's I would say if you're interested in GASPI, there are better tutorials for that. But if you're interested in matrix factorization, high performance matrix factorization, you can check out the code on GitHub. Right. This slide I showed before, so we've tackled like the right-hand side. We managed to build a model for the whole matrix, but we also wanted to include compound features. We want to enhance the model by using the shape, the 3D or 2D shape of the compound, for example, to make better predictions. So what we had to do for that, actually, we took this BPMF implementation, which is very high performance, very well optimized, and we stripped it down to the bare minimum single nodes. And because we saw this was the only way we could, we needed to focus to add those new features. We needed to focus quite a lot on code maintainability and extensibility, a lot more on code engineering than on high performance engineering. So we turned this BPMF implementation more into a framework. The framework is called SMURFF, and it can deal, as you see on the top left, it can deal with factoring multiple matrices of different types, with different noise models, with different algorithms, with side information or without side information. So that it allows us to do like many different types of algorithms or combinations of algorithms, like group factor analysis or Macau, which uses a solver to take into account side information. And we could experiment by mixing and matching different algorithms or different parameters in the SMURFF framework. So it became less of an HPC toy and much more like something which is useful for the actual users, which in this case, like the pharmaceutical companies are using this internally. We have academics that are using this framework to do the research. So, and then what is important for those people is, besides the first line, many matrix and tensor factorization methods and maintainable, right? It's still using C++ with OpenMP, with MPI, but it's a lot less HPC and a lot more stripped down with a lot more focus on maintainability. But most importantly, it's easy to use. You can install it on your laptop using one single command. If you go to the website, it's also on GitHub, and there is documentation, which is also important, of course. There are notebooks which you can use to make a tutorial, and you can do the notebooks on your own laptop, and then you can scale out if you want to a cluster. So it's very important for the data science, bioinformatician people to be able to try things out on their laptop using this notebook interface, and then scale out if they want to supercomputing, right? So this was one of the very important step forwards to get acceptance for this matrix factorization implementation. To put things into perspective, the performance of SMURFF, although it's less than BPMF, it's still good. So you have on the top line, you have the performance. So lower is better in this case. So the y-axis is a logarithmic scale of runtime, and it shows you from different number of cores implementation of the same algorithm in different frameworks. So the top one is a Python framework written completely in Python, but very flexible, that can do a lot of algorithms. So, and then the orange one, GraphG, is a C++ framework, less flexible, but still quite a lot written in C++, multi-core, still quite fast. But you can see that for the SMURFF framework is still 15 times faster than this C++ GraphG framework. And then if you go to the really multi-core, multi-node BPMF with GASPI, that's still 37 or 3 orders of magnitude faster than SMURFF. So this is kind of expected. The more you optimize your code, you can really gain. If you go to very specific HPC code, you gain a lot of performance by losing adaptability or by losing flexibility. We integrated this into SMURFF into a parameter exploration. So we did a lot of hyperparameter exploration to find the good initial conditions or the good parameters to build the model. We built many different models in XGROOST using HYPERLOOM, which is another workflow manager that we implemented in XGROOST. We compared the results of SMURFF with XNet, which is a deep learning based model. We also compared them to single task models. So they only looked at those single task models. They only look at a single target at a time. So the SMURFF and XNet, they built a model for the whole matrix, while SVM, random forest, and gradient boosting only they build a model for only a single target, a single column in the matrix. And in the end, we went to compare all of these models. And so we did this is one of the most interesting slides of the whole XGROOST project, which is this showing for each of the targets, each of the protein targets, which one of the methods is building the best model. And you see most of the cases, the XGBoost, which is a single target model, is still building the best model. As I said, SMURFF still has its advantages, like giving you confidence interval. So it's still actually being used inside the pharmaceutical industry because this is models on public data. It turns out that SMURFF is still quite good in making models on private data. So although this slide kind of says like you should always use gradient boosting, no, it's not that simple. It's what this slide kind of shows is like one of the things I like to say here is that deep learning is not the answer to everything. You should really look at what does my data like, what is my data like, what are the best parameters to tune, and what is the best algorithm to use, and it will all depend on the conditions. And I don't think deep learning is the answer to everything, right? To finish off, I'd like to show a bit what we're doing towards the future. And this is one of the things we're doing in the EPIC project, where we're looking at adapting the algorithm, the BPMF algorithm, to make the algorithm more scalable. So as I said, BPMF is hard to scale. The BPMF is hard to scale, but the algorithm is very hard to scale because each time you You add more nodes, you cut the data in half, you increase the communication and you reduce the computation per node. And in this case, what we did is change the algorithm. So first you build a model on a subset of the data of the matrix. You build a subset, you build a model on only one portion of the data, which you carefully select. It's called this Y11, and then you propagate this model to the left-hand side in the blue Y matrices, and you propagate the model to downwards, and you build a model for the others, the blue subblocks of your matrix. And then you can do that in parallel without any communication. And then you can build a model for each of the green subblocks of your Y matrix, and you can do that without any communication in between the blocks. So this is some algorithmic changes that we're doing or investigating that really allows you to limit the amount of communication. And the other thing which we're doing is taking those models, and then so we have a lot of these models to do compound activity prediction. And then what the pharmaceutical companies wanted to do is something called virtual molecule screening. They constructing a lot of billions of artificial molecules, which they don't need to make into the lab. They just need to generate a description of the molecule. And then we have a very efficient system to generate target predictions for all of those billions of generated molecules using the models that we made in the ExCAPE project. And in the EUREXA and EPIC project, we're mapping this prediction pipeline on FPGAs and GPUs. And we've seen that this prediction pipeline is a very good candidate to be accelerated on FPGAs and GPUs. So conclusions. So I've talked about compound activity prediction in the ExCAPE project, and how one of the methods is called matrix factorization. I've shown you how to optimize BPMF with GASPI and how the help we've gotten by the POP CoE. If you want to use SMURFF, I would say go to the GitHub repository. There are instructions there on how to use and install SMURFF. And as a last piece, I talked about virtual molecule screening on GPU and FPGA. Before we go to the questions, I have one more slide. We also made a video in the ExCAPE project. So, now that you know about all of the details, the video should be very easy for you to understand. If it isn't, then I didn't do a good job explaining what is compound activity prediction.
A million laptops wired together is roughly equivalent to the computing power of an exascale supercomputer. Exascale supercomputing power will enable much better predictions through machine learning. This is useful in many domains, such as the search for new medicines. Diseases can be cured by molecules that proteins. Experimenting with molecules to see if they heal diseases takes time and is expensive, so we cannot run all the tests we want to. If we can predict the binding of all drug molecules to a disease protein based on what we know from a few experiments, then we can compensate for missing tests. This vastly improves our chances of finding a molecule that works. Building a predictive model for a single protein works well if there is enough data. However, for some proteins, there is not enough experimental data to make a model by looking at that protein alone. A good approach is to use all data from all proteins simultaneously. This is known as multi-target machine learning. Doing all this on a supercomputer needs new math, better programs, and the right input data. The XGROOST project is a collaboration of researchers to learn how to make predictions using exascale supercomputers. Being able to work with the best from across the EU allows us to tackle these tough scientific challenges for the benefit of everyone. First results from the project are already being taken up by the pharmaceutical industry partners.
Okay. I think there's still some time to put some questions into the questions box. Otherwise, I think I'll continue. So, John, is it okay that I read the questions and then I answer them speaking?
Yes, that's fine, yes.
I don't have to type the answer, right?
No, don't type the answer.
Good. Okay, first question, how to determine if the compound has been bound to a protein? Is it through the binding free energy? So actually what we do here is we do machine learning, meaning that we have a lot of data where we know that what is the, I think that it's using PIC50 values, which is a kind of a metric of how well a compound binds to a protein. It's a known bioinformatics metric that we're using, and we're trying to predict this metric by using existing values. Existing values coming from publications. There's large databases which have been of compound activity information, that databases that have been made based on publications that we do on that's the public data, and then the pharmaceutical industries or companies themselves have large internal databases where they collect similar information from chemical experiments, right? So did you take a look at the weak scaling behavior of MPI versus GASPI? No, I didn't. I could do that, but I don't. Yeah, it will be interesting. Maybe I have some data there, but I didn't. I didn't look at the weak scaling. And then performance difference between TBB and OpenMP version. That's an interesting question. So we made an OpenMP version quite some time ago, and we also made a TBB version. And the TBB version was quite a lot better because it has a much more sophisticated runtime that intelligently allocates tasks to threads. But and then TBB was a lot faster than OpenMP. But now with OpenMP tasks, you have something similar, or you have actually the same behavior in OpenMP. So now there is no difference anymore between the OpenMP and the TBB version in terms of performance. And I've since a couple of versions ago, I've dropped TBB support because I don't want to maintain several versions, and OpenMP is more widely accepted than TBB. And the performance is as good. So I only kept the TBB, OpenMP version. Did you monitor the threads behavior of GASPI implementation with X-Tray and Paraver? No, I don't know if it's possible. I think all the X-Tray and Paraver monitoring was done on the MPI version. And so the optimizations that we did with MPI collectives were done, well, taking into account what could be the GASPI version, but we didn't make, I don't think we made any X-Tray or Paraver measurements on the GASPI version itself. And then the last question, hardware characterizations of the machine used. Wow. A standard Intel-based cluster. Intel TBB is not portable. He says. Well, okay, I don't know. I don't know what about the portability of TBB and OpenMP, and I would say since OpenMP is more widely accepted, it makes sense to standardize on OpenMP, which is what we did. This was the last question. So with this, I would like to thank you. Feel free to check out SMURFF, BPMF, and GASPI. And thanks you all for listening.